Alright, so let's start the third and the last video of this chapter, IEEE Standard Floating Point. IEEE Standard Operation, why is 1 divided by 0 worth to be infinity and not minus infinity? To answer this, you have different numbers for 0 and minus 0, so that a divided by 0 is infinity and a divided by minus 0 equals minus infinity. The test 0 equals 0 is true, and the test infinity divided infinity equals minus infinity is false. The square root of a negative number is an invalid operation. There is no other relation for variables that receive not a number. Overflow occurs when the result of the operation is finity, but with an absolute value greater than the largest available floating number. In IEEE standard, the result of overflow is nmax, or plus or minus infinity, depending on the round model. So think about that. If you have some doubts, please ask me. Underflow occurs when the exact value of an operation is not zero, but has an absolute value less than the smallest normalized floating number. In IEEE standard, the result of an underflow is a number subnormal, n minus or 0, depending on the round mode. This process is known like gradual underflow. So all these sort of operations, of course, it's some rules for some exceptions. So this is quite tricky, So pay attention here, please. Consider the following operation use IEEE single standard. The second operand is n min, and the first is slight higher. So if you are going to use 1.01 minus 1 to both of the numbers is elevated to 1 minus 100 and 126. The result is 0.01. If you normalize, you are going to have 120 negative. But it's not possible to represent in single format. So, if no gradual overflow, the result of example 13 would be 0. The collective value can be stored like that, because you can make use of subnormal numbers. So invalid operation, so this is some exceptions. So there is so you cannot use letters, characters, or 0 divided by 0, and so on. So you have got an invalid operation. So the result is going to be not a number. Divided by 0, integer number divided by 0 are going to have plus or minus infinity. Overflow, you have plus or minus infinity or plus or minus nmax. Underflow, you have subnormal minus 0 or n minus. Inexact, so you have some amount round correctly. Table 3 summarizes the IEEE standard response to 5 exception types, as you can see here. So just what happened here in the process of cancellation. Consider the two numbers. Both numbers are represented by the representation of pi. The first number is a 6-digit approximation of pi, while the second number agrees just with two 12 digits. The difference is the equation 23 here. If the difference is calculated accurately in C-SIGO, the result would be 0, no difference. The difference between 23 and 24 that first converts the next bound number to binary, then truncate that value to be able to store. In single format, these two values are equals. In the double format is used, the result will be different. So you are going to have some quite equal to the correct number. Look, the equation 25. The value 5 agrees with 3 digits in 23. What is the meaning of all the digits? The answer is that the value 25 is the rounded difference between x and y. The ordered digits are spurious. In this case, we say that there is a loss of precision in computation. Z equals x minus y, regardless of whether there is a complete or partial loss of accuracy. This phenomenon is called cancellation. Cancellation. An example of cancellation can be obtained by approximating the derivative. Let f, a function of r towards r, be a continuous and differentiable function. How can an estimate of f be made? So the derivative of f be made. By definition, we have the equation 26, a representation of derivative. A natural idea is to evaluate 26 for a small value of h. But how small? We show a program in which the value of h is defined for the range of 10 minus 1 to 10 to minus 20. In this case, we know precisely what's the value of derivative of sine x in x, which is cosine of x, and so one can compare the results. The absolute value of the difference between the value calculated by 26 and the correct value is called error. So here in the book, this exercise is made easy. I have made here a conversion to MATLAB to make perhaps easier for most of you, but you can also use Octave if you don't have access to MATLAB. So the exercise here this program here is not so difficult, but it's very, very interesting. So initial parameters, x equals 1, the step age equals 1, n equals 1, and derivative is the correct answer is constant of x. So here this is just going to explain in the screen, and here is the program. So it's using while, you can also use for, that's no problem. We are going to use age divided by 10. So each time, each step, you are going to have 1 divided by 10. So you are going to have 0.1, and after that 0.01, and so on. So if you are going to make an approximation of the result, you can use this equation here, right? So this is the approximation of the result. And the error is the absolute value of the correct answer that is calculated here, and the approximation between the correct answer and that solution obtained by an approximation of the derivative. So this small program is going to show what the cancellation occurs in a computer. So this is the values. As you can easily see here, the error is going down, but when the step is approaching around -9, the error becomes increasing again. So this is really important to see. In a graph, it's make easy to see that. In a logarithm graph, if we reduce the step age, what's going on here? The step age, we are going to reduce these values, as you can see here. So what's the main message of this calculation? You cannot reduce step age. Usually this step is used, for example, in computer simulation, in a SPICE, in Multisim, and even in LabVIEW. You can set up this step to solve some differentiation. So it's not useful, and sometimes it's worse to reduce this parameter to a very small numbers, because instead of reduce the error, you can increase. So the error is shown in figure 57 as a function of age, use a logarithmic scale. The result is quite interesting. It's not that the error decreases as the value of h becomes less, as expected, but this phenomenon course to a certain extent. When h becomes small too much, the approach gets worse. Because what? If x1 equals 1 and h is less than half the precision of the machine, 10 minus 16, so x plus h, that is, 1 plus h, is round to 1, and the value of sine x plus h and the sinusoidal x cancel each other completely. This question can be summarized as follows. This is the most important result of this part of the course, when you use h very large, a high discretization error is faced. But when you use h very small, a high cancellation error appears. So this is the main message of this slide. For the fx sine x function with x equals 1, the best choice for h is around 10 minus 8, roughly the square root of the machine's accuracy. Right, so this is the exercise 5, and I hope that it can be very tricky for many of you, but I'd like you guys to calculate this recursive function. So the first number is here, x0. This is big number here. There is a reason to be calculated like that. So pay attention, there is a negative part here. So we are going to start the x0 with this number. And after that, you are going to calculate the next number. Replace x0 in this equation, right? This is called logistic equation. The sequence is given by xn. So I'd like to calculate this sequence 1n approaches infinity with this initial condition. What's going to be the stationary or the permanent solution of this equation? I hope that you can use the majority of knowledge that you have seen here in this course to come up with some solutions, some conclusions of what's going on here. So you can use, please, Octave, MATLAB, but you should use, of course, floating point programs to make this calculation, and make some considerations and try to discuss your team to see what's the final result of this equation here, right? So, okay, so this is the last video of this chapter about the standard point flight, and I hope that you have joined, and if you have any question, please you can ask by email or even in our online meeting. Thank you very much